In this presentation, I'm going to provide an overview of PCSWM's real-time flood forecasting system. Recently, we've been working with two conservation authorities in Ontario to develop this system for their watersheds, and that's the Toronto and Region Conservation Authority and the Credit Valley Conservation Authority. In terms of the Toronto and Region Conservation Authority, we've had the pleasure to work with Michael Haralal and Lorian Farrell on both the Don River and Etobicoke Creek watersheds. For the Credit Valley Conservation Authority, we've worked with Neelam Gupta on the Cooksville Creek watershed. The main problem we're trying to resolve is to improve the accuracy of flood forecasting. And the way we're trying to accomplish that is through much more detailed, higher resolution hydrologic and hydraulic modeling, higher resolution remote sensing radar rainfall acquisition and processing, real-time forecasting and flood analysis tools, and wrapping all of that up in an accessible spatial decision support environment. But first I want to provide a little bit of background about the conservation authorities we've been working with. In Ontario, there are 38 different conservation authorities, and their jurisdictions generally coincide with watershed boundaries. Their responsibilities include, among many other things, flood management and flood warning. In the case of the Toronto and Region Conservation Authority, their jurisdiction encompasses 9 watersheds which are home to about 3.5 million people. These are the watersheds that we've been working with. Starting from the west, there's Cooksville Creek watershed, which is fairly small, about 36 square kilometers, but very highly urbanized. Then there's the Etobicoke Creek watershed at about 200 square kilometers, and the Don River watershed at about 360 square kilometers. The key technologies that we're working with is the NOAA's NEXRAD Weather Service Radar 1988 Doppler system, US EPA's SWMM5 engine, and for developing the decision support environment, we've created that in HTML5, which is the new markup language, and Google Earth, Google Maps. PCSWM is the software that provides the glue to hold all of this together. And PCSWM, for those of you who are unfamiliar with it, has been around for about 25 years, and it's a spatial decision support system for the US EPA SWMM5 model. For those of you who are not familiar with SWMM5, it does both hydrologic and hydraulic modeling of both quantity and quality, and it's typically applied to stormwater drainage, wastewater drainage, or watershed drainage systems. It's a physically based deterministic model that excels at long-term continuous modeling and dynamic wave analysis. PCSWM 2011 Real-Time uses the official US EPA SWMM5 engine for all hydraulic calculations. It itself is based around a high-performance GIS engine, which lends itself very well to some of the topological operations that we have to do in this flood analysis. And it's based around open standards, so there's no data migration required. It's a standalone product, so there's no additional licenses required, and it has a proven track record. But most importantly, it provides very efficient solution of complex modeling. And that's a good thing, because what we're trying to do is very, very computationally intensive. One of the things we do have on our side, though, is the vast improvements in computational power, and I'm not sure that many people appreciate just how powerful our computers are if you are able to leverage that full power. Over the 25-year history of PCSWM, when we first started out in 1984, the current computers of the day could do about 10,000 floating point operations per second, which is a measurement of computational power. If you contrast that to today, in 2011, the modern typical computers can do about 100 billion floating point operations per second. That's 100 million times more powerful. Now, if you combine that in conjunction with the ability of PCSWM to create a computational grid, which is essentially using a network of computers to act together as a single supercomputer, our computational grid at CHI, a modest one of about 10 computers, has a theoretical maximum floating point operations of about 1 trillion per second. And that's a lot of zeros. So if you think about that, let's say you were able to accomplish one mathematical operation per second. And you did that for your entire working career, every day, every second, for 40 years. You'd get up to a pretty impressive number of about 300 million calculations. Well, that's less than a third of what a current computational grid can do in a single second. So to go over the system that we have, I'm going to talk a little bit about the 4 different components. And that's radar acquisition and processing, real-time flood modeling, flood inundation analysis, and the web-based spatial decision support system. I'm going to focus mostly on the first 2 components, as they're the most technically interesting. In terms of radar acquisition and processing, for this study we've been using the NEXRAD weather radar station at Buffalo's International Airport. It provides excellent coverage for most of southern Ontario, and as you can see with the red extent for Cooksville Creek in this map, it's about halfway along the coverage area, and the coverage area has a radius of about 240 kilometers. And what the product is that we get back is base reflectivity data, or a measure of microwaves bouncing off of particles in the atmosphere. And the resolution of that, or at least the spatial resolution, is about 1 degree by 1 kilometer. So as you move away from the center of the radar station, the cell size gets a little bit bigger. The temporal resolution is about every 1 scan every 5 minutes during wet weather. And as you can see, this resolution is vastly superior than the typical resolution you get from a network of rain gauges, and it allows you to see the spatial variations in rainfall between the gauges. In this view, the gauges are represented by blue cylinders. But however, rain gauges are fairly accurate, or at least one of the best tools that we have at measuring point rainfall amounts. But they're very poor at telling you what fell even half a mile away. Whereas the radar data gives us that nice spatial variability in rainfall. But because radar is being sampled in this area, it's about 1 kilometer above our heads, it's hard to correlate that with actual rainfall that falls on the ground. So by combining these 2 products, we hope to create a product that is both gives us spatial variability, high temporal variability, and is as accurate or more accurate than what the rain gauge network gives us. I'm going to go into the accuracy of that rainfall forecasting in a few slides, but assuming we can get reasonable estimates of rainfall, we next need to track the speed and direction, and so we can forecast forward in time for our forecasted period. PCSWM has algorithms for doing that built into it. We can also rely on the NEXRAD weather radar system's estimates of speed and direction. So now let's talk a little bit about the real-time flood modeling. Typically, if flooding is an issue, there's been past work been done on delineating flood lines, and we want to be able to leverage those data sets. So we built a very good importing tool into PCSWM for importing existing HEC-RAS models. In the case of the Don River watershed, we imported 42 HEC-RAS models, which were about 3,000 transects, 270 bridges, representing about 225 kilometers of natural channels. There was also 1 dam in the system that had real-time control that we had to include in the model. The solution method for routing is SWM5's dynamic wave routing, which handles surcharging, backwater effects, even reverse flows, as solves the full St. Venant equations. In terms of the hydrology, we broke the area up into 70 subcatchments, and we parameterized those subcatchments using GIS layers for land use and soil type. There's also a lot of detention storage in the upper areas of the system, and so we created pond storage and discharge curves for those. The solution method for the hydrology is SWM5's nonlinear reservoir routing method, which is physically based, and we adopted the green and amp infiltration method, again a physically based method for estimating infiltration. So out of interest, we wanted to compare the water surface elevation produced by SWM5's dynamic wave with the original HEC-RAS steady state results. In this profile, you can see the blue area is PCSWM's water surface elevation profile. And the red dashes represent the water surface elevation that was created by the HEC-RAS steady state analysis for the 100-year event. If we zoom in to the area around the bridge, you can see we're doing fairly well, although there's a bit of a discrepancy at the inlet for the bridge. And those are probably caused by local losses. Of course, if we wanted to calibrate this to the HEC-RAS results, we could do that simply by adjusting the local losses in the SWM5 model. And you can see we end up getting a very good match. To provide another comparison, we can look at plotting the SWM5 maximum HGL results against the HEC-RAS water surface elevation data points. In this plot, we're looking at one of the HEC-RAS models. It contained 3 reaches. And you can see the correlation between the two. However, as interesting as that is, we want to calibrate the model to observed flows. In the area we had 9 rain gauges. 4 of them were within the watershed and 5 of them were immediately adjacent to the watershed. And we had 3 flow gauges. And we ran the model with 7 different radar rainfall techniques. We validated the model against 10 significant events. This is one of them. It's about a 50 millimeter event, and we evaluated all the 7 different ways of combining radar data and rain gauge data. And you can see there's quite a variation in the flows. However, I want to draw your attention to the green line. It's one of the products that was consistently very good. And if we compare that to the red hydrograph, which is our observed, you can see that the general shape is very good, both in the rising limb and the receding limb of the hydrograph, although in this particular event we are overestimating the peak flows a small amount. If we look at a scatter plot for all the 10 events that we looked at, and we're plotting the observed maximum flow against the computed maximum flow, you can see the one product that we settled on actually does very well. It's highlighted with the red circles. All 10 events were within plus or minus 20%, and 8 of the 10 events were actually within plus or minus 10% of the observed peak flows. So that's it for real-time modeling. Let's move on to the flood inundation analysis, or what we do with the results of the SWM model. There's a couple things that we look at. One is a flood vulnerable asset analysis, which looks at the buildings that are within the floodplain. And we have threshold elevations for flooding defined for each of these buildings, and we compare that elevation to the closest point on the river through an interpolation between the water surface elevation points generated by SWM5. In this plan view, you can see the center line of the river is the blue line, 100-year flood lines are the orange lines. And we've color-coded the building footprints in real time to indicate their likelihood of being impacted during the forecasted period, with green being not likely, yellow being more likely, and red being fairly likely to be impacted. You're also able to drill into these buildings and pull up elevation detail as well as the predicted flooding depth and the time of maximum occurrence. You can also see in the background that we've overlaid another product, which is the flood inundation polygon. And that's calculated from a DEM and comparing that against the water surface elevation profile produced by SWM5. And we do this quickly enough that we can actually animate this and play back the real-time simulation in real time. And if we look at the web-based spatial decision support environment that we developed, it's very portable and accessible from anywhere. This is it running on a desktop computer. This is it running on a smartphone. This is it running on a tablet computer. It supports multi-touch and gestures. This is it running on a wall-mounted display. And it has varying levels of user permissions for access to the data. It also has a public education component to it, where the public can look at historical events in their watershed. That's a brief overview of PCSWM's real-time flood forecasting system. If we want to take a look at how the system downloads real-time weather radar data from NOAA's server, usually it takes less than a minute from the time that the scan actually takes place at the radar station to when that product is available. And that's downloaded immediately and processed against the rain and flow gauge real-time network to calibrate that to the rain gauges. That's all stored and archived in a radar rainfall repository for historical access in the future. And the PCs from real-time flood inundation forecasting does the forecasting and flood modeling and produces the results that are available in the web interface and also the various desktop interfaces for PCs from real-time. Thanks a lot for your attention, and if you have any questions, please visit our website at chaiwater.com.